You've heard black holes crush you to infinite density, spaghettify you, destroy information itself. But what does crush to infinite density actually mean? What happens to your atoms, your particles? Do you experience it? Does anything escape? And why do physicists argue about whether information is truly destroyed? The usual answer, infinite density, is just a mathematical singularity, a place where our equations break down and start giving nonsense answers. The real story is stranger. It involves time itself stopping, horizons that behave differently depending on who's watching. What kills you has nothing to do with the singularity. It's about what happens at the horizon and who's measuring. Everyone imagines the same picture. You fall through empty space, gaining speed, until suddenly at the center, crushing. Wrong. Well, partially wrong. There are actually two separate questions here: what you experience as you fall in, and what a distant observer sees watching you fall. Already this is strange. Same event, completely different descriptions depending on perspective. Let's start with you. You're falling in. What do you actually feel? Not crushing. Stretching. Gravity is stronger at your feet than your head if you're falling feet first. This is the tidal force. For a small black hole, stellar mass, say 10 times the sun, the gradient is enormous. It rips you apart far outside the horizon. Your feet accelerate faster than your head. The difference exceeds the strength of molecular bonds. You're torn into a stream of atoms long before you reach the point of no return. But for a supermassive black hole, the kind at galactic centers, the gradient is gentler. A black hole with 1 billion solar masses has such a large radius that the tidal force at the horizon equals Earth's surface gravity. Nothing special. You'd feel no stretching at all crossing the horizon. The mathematics tells us this. Tidal force is proportional to mass over radius cubed. Larger mass means larger radius, and the radius grows faster than the mass. So you might survive crossing the horizon of a supermassive black hole intact. Curiously, that's when things get truly strange. The horizon is not a place, not in the sense of being a physical barrier you can touch, like a membrane stretched across space. It's a light-like surface, the boundary where escape velocity reaches the speed of light. There's nothing special about the space there. No wall, no edge. From your perspective, falling through feels ordinary. Space looks normal. You see stars, but it's a point of no return. Once you cross, all your future paths lead inward, not because some force pulls you, because space-time geometry itself tilts. Imagine a river flowing faster than you can swim. Past a certain point, even swimming upstream at maximum speed, you still drift downstream. That's the horizon. Well, not exactly a river. Rivers have water. This is space-time itself flowing. But the principle holds, so you cross smoothly. Then what? How long until you hit the center? We can calculate this using Schwarzschild geometry. For a stellar mass black hole, 10 solar masses, from horizon to singularity, takes about 0.005 seconds. For a supermassive black hole, like Sagittarius A star, at our galaxy center, 4 million solar masses, about 20 seconds. For an ultramassive black hole, billions of solar masses, a few hours. That's your experience, your wristwatch, your heartbeat. During this time, space gets increasingly curved. Tidal forces grow without bound as you approach r equals 0. Eventually, every black hole rips you apart near the singularity, not at the horizon, near the center. Your atoms are torn apart, then the nuclei, then quarks are crushed to, we don't know. Our equations give infinite density, but that's where general relativity breaks down. We probably need quantum gravity to describe what actually happens at r equals 0. In 1965, Roger Penrose proved singularities are inevitable inside black holes, not artifacts of symmetry or special conditions, genuine features of gravitational collapse. The mathematics forces it. From your perspective, the journey is brief and terminal. Now let's watch you fall in. From outside, from safety. This is where time becomes slippery. I'm watching you fall toward the horizon with a telescope. You fall faster and faster, approaching the horizon, but as you near it, I see you slow down. The light from you becomes increasingly redshifted. Gravitational redshift. Time dilation approaches infinity at the horizon. The result? I never see you cross the horizon. You appear frozen, asymptotically approaching but never reaching. Your image fades to darkness as the photons are redshifted beyond detection. From my reference frame, you take infinite time to cross the horizon. Same event, two descriptions. You say, I crossed the horizon 20 seconds ago and I'm being torn apart. I say, you haven't crossed yet and never will. Both correct in their own reference frames. This is not an optical illusion. It's fundamental to how time works in curved spacetime. Gravitational time dilation has been measured with atomic clocks at different altitudes. GPS satellites must correct for this. Their clocks run faster than ground clocks by 38 microseconds per day. Without the correction, GPS would fail within minutes. Near a black hole, the effect becomes extreme. The time dilation factor is 1 over the square root of 1 minus 2 gm over rc squared. At the horizon, the denominator goes to 0. Time dilation goes to infinity. So do you cross or not? Is the horizon real? The horizon is real. You cross it. But from outside, the crossing takes infinite coordinate time, both true simultaneously. Classical general relativity says you and your information fall in and disappear forever. A black hole has only 3 properties: mass, charge, angular momentum, spin. Everything else is erased. What fell in, when it fell in, how it was arranged. The no-hair theorem says black holes have no distinguishing features beyond M, Q, J. Throw in an encyclopedia. Throw in the same pages, scrambled. Same final black hole. Information appears destroyed. The problem, quantum mechanics says information cannot be destroyed. The unitarity principle. Total information in the universe is conserved. Evolution must be reversible, at least in principle. In 1975, I discovered black holes evaporate via quantum effects. Hawking radiation. Particle-antiparticle pairs form at the horizon. One particle falls in, one escapes. The black hole slowly loses mass. Eventually, it evaporates completely. The paradox: if the black hole evaporates completely and Hawking radiation is thermal, random, where did the information go? Thermal radiation carries no information about what fell in. For decades, I argued information is destroyed. I was wrong. Probably, quantum field theory in curved spacetime tells us the vacuum isn't empty. Virtual particle-antiparticle pairs constantly form and annihilate. Near the horizon, one particle falls in with negative energy relative to infinity. The partner escapes with positive energy. The black hole loses mass equal to the escaped particle's energy. The temperature is inversely proportional to mass. A stellar black hole has a temperature around 10 to the -8th Kelvin, far colder than the cosmic microwave background. It won't evaporate for 10 to the 67th years. A tiny black hole, mass of a mountain, has a temperature around 10 to the 11th Kelvin. It evaporates explosively in a fraction of a second. We haven't directly observed this yet. The radiation is too weak for astrophysical black holes, but analog systems show similar radiation, sonic black holes in fluid flows. In 2016, Jeff Steinhauer created an acoustic black hole in a Bose-Einstein condensate and observed analog Hawking radiation. The evaporation suggests black holes aren't permanent, which brings us back to information. Where does it go? In 2012, Almheri, Marolf, Polchinski, and Sully proposed the firewall paradox. It forces a choice between 3 principles. You can't have all 3. Unitarity. Information is conserved. No drama at the horizon. You cross smoothly, the equivalence principle. Hawking radiation is thermal. Their argument, if information escapes in the radiation, early and late radiation must be entangled. But late radiation should also be entangled with the interior of the black hole. Quantum mechanics forbids this. Monogamy of entanglement. The resolution they proposed, the horizon, must be a firewall, a violent region of high energy that destroys any infalling observer. This contradicts general relativity. You should cross smoothly. But information conservation seems to require a firewall. Many physicists find this unacceptable. Alternative proposals exist. Information stored at the horizon and released slowly. Black hole. Complementarity. Wormholes connecting the interior to the radiation. ER equals EPR. Quantum corrections modifying the horizon structure subtly. Information gradually leaking out in subtle correlations in the radiation. There's no consensus. I now think information escapes, but we don't understand how. It probably requires quantum gravity, a theory unifying general relativity and quantum mechanics. String theory, loop quantum gravity, other approaches all try to resolve this. None proven. Return to the original question. What happens when you fall into a black hole? It depends on the black hole's size and where you're measuring from. Your experience as the infalling observer. For a small black hole, you're ripped apart before the horizon by tidal forces. For a large black hole, you cross the horizon smoothly, assuming there's no firewall. Brief journey to the singularity. Seconds, 2 hours, depending on mass. Near the singularity, you're torn apart by infinite tidal forces. What happens at ER equals 0? Unknown. Quantum gravity territory. The outside observer's experience. They never see you cross. They watch you freeze at the horizon and fade to darkness. They see Hawking radiation slowly escape over billions or trillions of years. Information about you is somehow encoded in the radiation. Probably. The deep strangeness is that both descriptions are valid. Relativity teaches us there's no absolute simultaneity, no preferred reference frame. When did you cross the horizon? Has no frame-independent answer. For you, it's a specific moment on your world line. For me, it's never in my coordinate time. The connection to information. Maybe information doesn't need to escape in the traditional sense. Perhaps it's encoded in correlations across the horizon, or in the global quantum state that includes interior and exterior. We started with a simple picture. Fall in, get crushed. Reality. Which version of you are we talking about? Observer perspective matters. Fundamentally, all of this assumes general relativity is correct down to the singularity. It certainly breaks down somewhere. At the Planck scale, 10 to the minus 35 meters, quantum effects dominate. We need a theory of quantum gravity to describe the true nature of the singularity. How information escapes, whether firewalls exist, the structure of space-time at the smallest scales. We don't have this theory yet. String theory predicts fuzzballs, no sharp horizon, no singularity, just quantum fuzz. Loop quantum gravity predicts a bounce. The singularity is replaced by a quantum bridge. We don't know. The mathematics becomes murky, the physics unclear. What happens inside? Does the singularity truly exist, or does space-time do something different when quantum effects matter? That requires understanding gravity as a quantum field. Different story, more speculative. I've got to stop somewhere.